Hello, good morning, good afternoon, and good evening from Hydromet. We are very happy to have you all at today's session. You've all registered to our webinar on the topic of degrees of precision, the role of tilt in Pyranometer's performance. My name is Ella Joseph, and I'm really happy to moderate today's meeting with my colleague Damon, answer all of your questions, give you some of the insights from our experience, what we got to know in the many centuries of experience around our pyranometers. So maybe I will walk you through some housekeeping rules so that you know what to expect in the upcoming few minutes and afterwards as well. This session is recorded and is going to be shared with you. So the recording will be sent to you with an email after the session, most likely 1 or 2 days later. So you can always have a look into that and share with your peers or anybody who is interested in that topic. You can also submit your questions during the presentation, and I strongly encourage you to do so, so that whenever there's something that it's popping in your head and you have some more ideas or questions that you need to feel to get answers to, put it into the chat and we are going to answer them at the end of the presentation. Damon is going to hold the presentation about 20 minutes. We've planned with 45 minutes, so there's plenty of time for your questions, and we want to focus on your topics and what's interesting to you. So we are welcoming you to be very active in today's webinar. There are two key takeaways that Damon drafted for us, so you can already see what we are going to look into and get a bit more familiar with. So irradiance sensor misalignment influences performance data and falsely reporting low or high performance. Accurate sensor tilt alignment is controlled in the field. So these are the two key takeaways that we would like you to take with after the webinar, and of course, get more insights and get answers to your questions after the presentation from Damon. Damon, we can't hear you, unfortunately, for some
Sorry.
reason.
Thanks, Ella. I'll briefly introduce myself and then jump off camera so we can focus on the presentation. But I'm Damon Nitzel. I've been in environmental sensing for about 12 years post-graduating college, where I studied in biochemistry and how proteins affect our body. And since then, I've been studying and exploring the world around us and how the world impacts more agriculture and solar, but also us as humans. And I like to fly fish and smoke beef jerky and try and curate things like that. So if you see me at RE Plus this year and you want to have a chat about more than just pyranometer tilt, love to learn more about you too. And with that, we'll jump into the agenda here. So for today's webinar, we're going to start with a quick review on solar irradiance and how it reaches the modules and why irradiance is important to performance ratio. This will set the stage for us to appreciate the potentially significant impact that pyranometer tilt can have on PV site energy production and the value of the site. We'll clarify the difference in sensor tilt and tilt response and describe some physics of how irradiance changes with tilt, with some things to look for in irradiance data to indicate an issue with sensor orientation. We'll review some best practices to maintain sensor alignment and finish up with an open Q&A session moderated by Ella. And before we dive in, for any who joined before the first minute, just a quick note that this webinar is being recorded for rewatch and sharing later. So as you know, we're all here because we work in solar and we're harnessing energy from the sun to power our lives. And something happened and it won't advance. There we go. Okay. So the way that energy from the sun reaches us in solar modules is in a few different ways. And the largest amount of energy reaches the modules in the direct normal irradiance beam, typically making up something like 85 to 90% of plane of array irradiance on a clear sky day. The rest of plane of array irradiance is made up of diffuse and reflected irradiance caused mainly by cloud reflections or refractions and atmospheric scattering, or in other words, like the light of the blue sky that you see. And another unfortunately relevant source of diffuse irradiance this time of year is wildfire smoke, and there are lots of other different reasons that irradiance could reach your modules in different directions, but those are a few key ones. And when clouds are present, diffuse irradiance increases, and in complete cloud cover, the direct beam irradiance essentially goes to zero, or the same level as all the diffuse around it. And so you only have diffuse available for production. And to measure these components, we place pyranometers in different but hopefully familiar positions around the solar farm. These positions include global horizontal irradiance, or GHI, which is defined as direct measurement of the total energy that strikes the horizontal plane of the Earth, and is typically the best way to compare relative total available energy between sites. When combined with reflected horizontal irradiance, or RHI, or often RGHI, surface albedo can be calculated to model the amount of reflected energy available for bifacial modules. Plane of array and rear-facing plane of array, or often POA rear, sensors directly measure the total energy available for the modules to convert to electricity, rather than using the GHI value and albedo to estimate that energy with modeling such as with BV-SIST. And we use these core sensors because we have to account for the radiance reaching the modules from many different angles, and positioning the sensor within the site in the right locations around the module is really important to this part of is a really important part of site design and installation. And our core topic today, sensor tilt, ensures that once we have sensors selected and installed, that they measure what we expect them to. So why does measuring what we expect them to matter? Well, because irradiance directly impacts performance ratio. And as you can see in this simplified performance ratio equation, irradiance is directly and inversely proportional to performance ratio. This means that when irradiance readings are higher than expected, performance ratio becomes lower than expected, and vice versa. And we use performance ratio for a lot of reasons at sites, and I'll go through a few before we dig into how sensor tilt influences irradiance measurements. So when performance metrics drop below guaranteed thresholds, it can trigger financial penalties and contract disputes, reducing the return of investment from a site and potentially damaging reputations. Low performance ratio serves as a red flag for something or some things that are not working on site, not working as expected on site, and can kick off a chain of analytics and diagnostics, which can result in site visits and corrective actions after root cause are determined and get things fixed. Performance is closely watched by investors, and when consistently low, it can shake the confidence in an asset's reliability and lead to reevaluation of the site's value. And eventually, low performance won't just be a temporary dip that we can fix. So that's a sign that the system is aging, and it's going to kick off discussions about repowering, redesigning, or even retiring parts of the site. And on the other side, when performance ratio is high, as you all know, hopefully, high performance metrics feel great. They're a confirmation that everything in the design, from layout to wiring and all the installation, was done correctly and everything is running smooth. When sites perform well, they build confidence to scale on. They give developers and investors green lights to replicate that success and expand portfolios. These times when performance is high allow the operations team to focus on preventative maintenance instead of running in break-fix mode. And this proactive mode lets the teams optimize performance instead of just chasing issues. A smoothly running site makes it easier to provide production forecasts to a utility who need reliable and accurate production forecast data to properly manage grid demand, which of course makes solar a more dependable part of the overall energy mix. And while these are just a few examples, I hope the takeaway that you get is, although governments sometimes struggle to affirm the following message, I truly believe that what we do as a solar industry is important. Our individual contributions matter, and we matter. And so with that, let's dive into sensor tilt, and let's start by clarifying the term sensor tilt and the ISO 9060 standard terminology tilt response. When we talk about sensor tilt or orientation, alignment, pointing direction, sensor angle, sensor level, or any other synonyms that can float in there, we're talking about physical alignment of the sensor. When we talk about tilt response, we're talking about how the sensor physically responds to changes in sensor alignment and the allowable variance that we as manufacturers need to design for per the standards when we pick detectors, material qualities, and control assembly quality. The Class A specification limit for tilt response is only 0.2%, and it's our job as manufacturers to take care of minimizing this error of tilt response. On the other hand, sensor orientation or sensor tilt is controlled and managed in the field, and it's one of the most impactful ways that users can contribute to accurate, reliable data. There's a few key things that influence irradiance measurements when a sensor is out of alignment. And the first and most obvious of those is the irradiance beam angle. Excuse me. As you would expect, when you tilt a sensor away from the sun, irradiance measurements go down. Although, as you'll see, if you're paying close attention in the north tilt slide, it isn't always as obvious when a sensor is tilted away from the sun at different times of day or season. And of course, the opposite is true. If you're pointed more towards the sun than, say, your modules, you can over-report irradiance, and that makes it seem like a site is underperforming when it's not. All Class A pyranometers have high-end optical glass or similar material domes covering the sensors. And despite the high clarity and uniformity these domes are required to have, they can still contain slight imperfections that alter how light enters the dome and ultimately how many photons reach the detector to create a signal. And the pyranometer on the right here has been deployed for a while. And if you look at the small reflections and things on the glass, the glass can get optical distortions over time being deployed, such as from sand pitting or scratching during maintenance, or even soiling on the dome, things like that. So lastly, there are thermal effects that can influence detector outputs and the way that heat transfers and reaches equilibrium, both inside the sensor and external to the sensor. And that can vary at different angles. And this can cause small changes in irradiance values. And by small, I mean on the scale of like 0.1% or less. So this isn't something that you should necessarily worry about, but the effects do exist and they contribute to the challenges we overcome manufacturing high-end pyranometers. So if you pretend the right side of this slide is south and the next slide is also south, what do we see when a sensor is tilted to the north? Intuitively, since the north tilt is away from the sun, total irradiance decreases. And in this example on the right side here, I simulated a 5-degree tilt, a little exaggerated on purpose to really show the point, using NREL data from July 2nd, 2025, and a Kippenzonen CMP22. And this graph might be a little unfamiliar for some, so I'm gonna walk through it real quick. On the y-axis, we have the irradiance intensity that's being measured, and on the x-axis, we have the zenith angle, which for a GHI sensor is the angle between directly pointed at the sensor, or the sensor normal vector, and the direct normal irradiance vector based on where the sun is in the sky. And at the equator, that angle goes to 0 in the middle of the day. But as you can see in this graph, in Golden, Colorado on July 2nd, it only goes down to 16.7 degrees away from directly above the sensor, which is also where you see the largest difference in irradiance on the top left of the graph here. And in this test case of 5 degrees tilt, which is again intentionally exaggerated beyond what you might see on a site so you can see it, the difference in daily total irradiance is about 1%, but the difference around solar noon is almost 3%. And if we change that tilt error to only 0.5 degrees, it's harder to see the differences in the graphed lines between leveled and misaligned data without zooming in. But this is what that graph would look like at 0.5 degrees. And the daily total difference in this half-degree tilt is around 0.8%, and solar noon difference is around 0.24%. So also note the secondary y-axis change here went from plus or minus 20 to plus or minus 5. So instead, if you tilt the sensor to the east, a GHI sensor, where the GHI sensor is pointed more towards the sun in the morning, unsurprisingly, we see over-reporting in the morning because it's looking more at the sun. And then in the afternoon, because it's tilted a little away from the sun, we see under-reporting in the evening. And while spot measurements are near 0 at solar noon and increase significantly as zenith angle increases, the daily total differences mostly cancel out, at least in this imperfect simulation, and that comes in at only 0.5% daily total difference. I'll look to back up this simulation here with some physical tests for future discussions too. This means that hourly production forecasts that are using GHI sensors with an eastward tilt are going to underreport production in the morning, be about right in the middle of the day, and then overestimate production in the afternoon. And overestimating production could lead to power supply shortages and even brownouts if grid balancing is too tight. So it's important that we get our sensors tilted and give our utilities the right information to do their grid load balancing. And similar to the north tilt, if we reduce this simulation to 0.5 degrees instead of 5, the lines tighten together a little. It's a little harder to see that there really is over-reporting and under-reporting in the morning. And then I'm sorry for not making them dotted, but the curved lines that kind of form this bell shape are a representation of the difference in morning and afternoon compared to the leveled sensor. So continuing the theme that sensor orientation affects irradiance based on relative sun position to the pyranometer, how orientation affects plane of array irradiance depends on a lot of variables such as the site's latitude, the time of year, how the modules are mounted, if the racking is fixed tilt or tracked. In places like Colorado, where NREL data we just reviewed was collected, the sun swings pretty far in the north summer mornings and evenings, which means a center tilted north can pick up more irradiance than expected. On fixed tilt systems, tilt errors tend to be consistent, showing up the same way day to day. However, on the seasonal time scale, and because the sun's path changes throughout the year, a tilt that may be okay in the winter might cause some bias in the summer, especially early and late in the day. On tracked sites, the misaligned sensor rotates with the tracker. So for a sensor tilted north, it could be more aligned with the sun in the morning, but less so at noon, resulting in a bias that varies hour by hour, as well as by season and by latitude, which makes it really difficult to spot errors just reading the data. And a POA pyranometer mounted on a tracker with an east or west tilt error should consistently under-report direct beam irradiance throughout the day because it follows the sun off a little bit instead of pointing directly at it. And as you might be thinking now, there's a lot to consider as far as sensor tilt. So how do I practically manage sensor orientation? And the first step of that is to ensure that you can monitor sensors tilt over time and that you're using a quality sensor. And so when we designed the SMP12, we built in an internal 2-axis tilt sensor that can be used during installation to level a sensor or to verify level after installing using a bubble level, as well as be logged to ensure that tilt stays consistent over time. And the SCADA software can use that data to set alarms for unexpected changes in sensor orientation, whether that's a stationary level GHI sensor or a POA sensor on a tracker that has a repeated pattern every day as it rotates east to west. There's 3 tilt outputs that can be logged, a global tilt that behaves like a bubble level, and then the 2 for roll and pitch tilt axis. And you can see in these diagrams the way that those 2 measurements rotate with the sensor. So if you get a sensor on your desk and get it connected to Smart Explorer or into Modbus Pull or something like that, where you can see roll and pitch values, and you can rotate around the cable axis or perpendicular to the cable axis and get a feel for how to control the sensor orientation using these 2 different axes. And then of course, the first step, as I mentioned, to ensuring this good tilt measurement is to get this a quality pyranometer with tilt measurement in it. So you should really make specifications that take this into account. And when you're writing requirements for your Class A pyranometers, you might want to include statements that define acceptable tilt deviation, that require documentation of sensor tilt at install, that require use of a sensor with 2-axis tilt for long-term monitoring. On the bottom here is a rough draft that you could start with to include tilt in the specifications. Additionally to the sensor itself, you should think about the environment around the sensor. So you might want to specify mounting hardware that minimizes drift or settling as you consider the environment the pyranometer is in. And for example, specifying that the MET station has a buried section rather than a pad-mounted attachment style on something like a 4-inch pad that might be susceptible to frost heave or runoff related settling. And if you have operational guidance in the design spec, you might also consider including periodic tilt checks in the operations and maintenance plans, or using tilt data to verify correct sensor alignment and adjusting it only when it becomes misaligned. So after you selected your sensor and you're ready to install it, We want to make sure that you use the right tools for the mounting application. For horizontal installs, the Kippen zone and bubble level is accurate to 0.1 degrees as long as the bubble is completely inside the circle. Even if the bubble's touching that black ring, it's still within that 0.1 degree. And of course, you could use the internal tilt measurement as well. And sometimes pyranometers get up on 10-foot towers, and it's difficult to get up above the sensor and look down on a bubble level. So you could use the digital output to level the sensor from below. And for POA sensors, it may make sense to use fixed tilt feet on the pyranometer and adjust the pyranometer mounting plate rather than the instrument to get the sensor oriented into the plane of the modules. Rather than getting creative on how to measure the north-south and east-west alignment of the sensor, it can be kind of challenging to get a level onto like the sensor body, or as you can see here, using something that you may have imperfect plastic, even though visually it looks pretty close. As you'll see, or as we've seen, even 0.2 degrees really makes a difference. So we want to make sure that we're doing everything we can to get these pointed the way that we want them to see. And again, if you have a laptop and a connection to the digital sensor with that 2-axis tilt, while you're putting something in POA, you can measure the east and west and north and south orientations on your modules, or even a few modules, and average them, because not all the modules point exactly the same direction. And then use that 2-axis tilt to point the pyranometer in the same orientation as your modules are. Something else to consider is to plan for install conditions. Often sites can be windy, and it's challenging to level a sensor while you're up on a ladder or in a bucket when the tower is vibrating or flexing slightly in the wind. So it might be necessary to return to do final leveling when wind speeds are lower. Once you get installed properly and you're reporting data, the installer can record the tilt measurements at the time of install as a commissioning step. And this will help set a baseline for SCADA alarms when tilt changes. And it helps performance engineers running tests be confident that their irradiance measurements are accurate as they look for missing performance before a site goes live, or after a site goes live and things are, performance is down. When irradiance abnormalities show up, adding in sensor tilt into the root cause analysis is something that we would recommend. And it might help to detect alignment shifts that are caused by winds or settling, or pretty commonly accidental movement during maintenance. There's a lot of stories of trucks bumping into a tower or hitting a cross arm, or a bird landing on something and moving things out of level. In the picture here, you can see a GHI pyranometer that was deployed level, but after a couple of years, the racking that it was mounted to tilted slightly, and which I think is likely due to the weight of the enclosures, causing the whole support structure to lean just a little as the soil gets rain and just that natural weight over time. And of course, after this photo, this sensor was adjusted back to level, but it was only detected during routine maintenance visit. And going forward, the tilt measurements are going to be used to detect any further changes in sensor orientation, so we don't have to wait for a maintenance visit. We can schedule one in order to get better irradiance data. And to sum up, sensor alignment is used in the it's in the user's control, sorry, and it can have a lot of large impacts on performance monitoring and the subsequent actions that we take when we try and correct performance, or what we do when performance is performing as expected. Irradiance data reliably increases when a quality Class A sensor with built-in tilt sensors is specified, then properly installed, monitored, and maintenanced. It's not enough just to pick a good sensor and get it installed correctly. You really have to pay attention to it and make sure that it stays doing what you want it to do. So with that, if you're attending RE Plus in 2025 in Las Vegas, Nevada, please come by the booth and continue this discussion. In addition to tilt, there's a lot more considerations to proper irradiance monitoring, and the poster that we're going to present at the show is aimed to help you understand what we as manufacturers design around, such as tilt response, and all the things users can do in the field to ensure best irradiance data, such as keeping sensors tilted in the correct orientation or alignment. So thank you for listening and being here. If you have questions, please go ahead and put them in the chat, and with that, I'll pass the lead back to Ella, and we'll try to answer any questions that you have.
Great, wonderful, Damon. Thank you for that presentation. We actually did get a few questions. However, if you still have any questions, don't hesitate to put them into the chat. We still have a few minutes to go. So, Damon, I would start with my first question. So, the question from one of our participants, which is, what are the implications of sensor tilt errors on long-term energy production forecasts?
I'm sorry, can you say that one more time? It cut out a little.
Yeah, sure, no problem. What are the implications of sensor tilt errors on long-term energy production forecasts?
So if you had, for example, if you had a sensor that was tilted where you're reading less irradiance than you're supposed to be, it would make you think that you might be producing more energy than you really are. And if you go for a long period of time with that, and then you go back and you sum up all the energy that you produced, and you may fall short of the total volume of energy. And if you think about it a little bit like water in a hose and the volume of water that you're pumping into a tank, uh, and that flow is a little slower than you thought it was when you got started, you may end up with less water in your tank at the end of the year. And of course, we're selling the water in the tank or the energy, not how efficient the site is to the utilities. So something like that might be a case, or obviously the opposite could happen. You could over-report performance. I think I said that backwards. You could under-report performance on accident and then be looking for problems that don't exist. And so you could be trying to go out to site and spending money on site visits that there's nothing really to find. It's just the irradiance sensor that needs to be, I suppose that is something to find, but it's just the irradiance sensor that may need to be adjusted. Those things like that.
Great, thank you, Damon. I hope that this answers the question of our participant. There is another one. Would it be possible to use the tilt measurements from the SMP sensors to check for tracking errors in the tracker?
I think so, and I guess by tracker you probably mean the single axis tracker. My brain immediately went to Solus 2 and tracking the sun movement for direct and diffuse irradiance. But yeah, I mean, so a lot of single axis trackers, I think probably all of them have built-in tilt measurements that help them control which angle they're pointing at. This would be an external third-party measurement that ensures that the row that you're currently measuring POA irradiance on is also tilting the correct direction. I could imagine a situation where you have one row that might not be the row with a tilt sensor in it that your pyranometer is on, and so your pyranometer ends up stuck in an angle where the rest of the rows in the array on that same tracker motor are tilting correctly, something like that. It's a rare situation, but a big deal when it happens. So keeping that tilt measurement and cross-checking against the actual tracker output could be a good thing to add into SCADA.
Thank you. Another question, Damon, is it daily dome glass cleaning required for the high accuracy?
So IEC 61724-1, I think 2021, requires for Class A sites, if you have like a really strict requirement to be certified in that IEC spec, you have to clean weekly. Baseline surface radiation networks clean daily, but that's not something that we typically see in solar. And I think a lot of just talking with people and experience, sometimes it's hard to get even weekly cleanings on site, especially for kind of those small to mid-range sites where they're not manned and they're 6 hours away from town and maybe they don't have anybody there for a couple of weeks. And those maintenance intervals can spread out a little bit. So, but the guidance for Class A is weekly.
Great, thank you. Another question, Damon. So here is about POA. How often should POA sensor tilt be checked or recalibrated in the field?
So if you're not monitoring tilt, I think my recommendation would probably be whenever you clean it, you should be trying to verify tilt. And if that's weekly, then that's awesome. But maybe monthly or quarterly kind of you should push for something on that kind of frequency. You absolutely should be checking on your met stations at least once a year. And nobody should be going more than a year between met station checks. If that's happening, there's other issues on site, like the site's been bought and they're transitioning teams and things like that, right? So realistically, how long can you go with irradiance data that isn't correct? And let's say it does get bumped by a truck and it's leaning 5 degrees, and you're underreporting performance by 1%. How long can you underreport performance by 1% before you go correct it? And that should help you, based on your site size and location and your contracts, kind of get a mental feel for how often I should be making sure this is correct. And then, of course, if you're monitoring over time, well, you don't have to go to site and check it. You can just look at the data and say, okay, we're still good, and that's the ideal.
Great. Another question, how do you ensure the tilt remains stable over time in harsh weather conditions?
Really, I think the answer is adjusting it. That there is going to be things, and the environment around us is pretty harsh, especially in the really harsh conditions, on the coast or in winter weather where you get heavy snow loads, things like that. Things are going to happen. Your sensor is going to come out of alignment, and going in and correcting that at the right frequency, and making sure that you understand when data is not tilted correctly or aligned correctly, and getting that fixed at a timely manner. And that's the strategy, I think. There has been a couple of like research designs for self-leveling tilt, but they're a little power hungry and moving parts in the field. I don't think we're quite to that point where that's something that can be offered commercially, although there is a commercial offering out there. So you could think about something like that. If that's something that would benefit you, I'd love to hear about that, push that back to the design team, and maybe help prioritize that kind of activity.
All right, great. And do you have any thoughts on matching panel tilt versus just using bubble level on POAs?
So a pretty common strategy for installing POA is to set the tracked sensors or tracked modules flat and then level at that zero tilt on the tracker. I think that's a pretty good strategy to get started. Having been on a few sites now, even in laying flat, sometimes the modules aren't all perfectly level with each other. So if you happen to be installing on a location where the module is slightly tilted and you're trying to align to only a single module, there's potential for some error there. I don't know how common it is. It might be 5% of the time or even less. But if you just go down the row, measure a few modules, go to the adjacent rows, measure a few modules, and you kind of get a feeling for what the average tilt is, that might be a good best practice to start implementing. And then of course, fixed tilt, you can't lay the modules flat, so you really need to understand what the average tilt of your module is, where the modules are pointing. And the purpose of that is your sensor is measuring irradiance that's representative of what your modules see. And when you run models on the irradiance values, you're trying to predict how much energy the modules are going to produce, and then divide what they actually produced by how much they could have produced to get performance ratio. So if you're not pointing your pyranometer in the same orientation as most of your modules, then you get a disconnect between that expected production and actual production.
Right. There are many questions, Damon. I'm like trying to filter out some that are coming few times and around the same topic. So another one would be, how stable is the internal tilt sensor? Does it require calibration? And if so, how often?
I think it's calibrated when the sensor's manufactured. I don't know the answer on if it needs to be recalibrated or not. I've had some sensors in my office for about 4 years now that still are right on zero when the bubble level is there, and because the bubble levels are within 0.1, and because it's in my office and not outdoors going through large thermal cycles, the bubble level is still very good. It hasn't evaporated at all, and the tilt measurement is spot on. And when you lay the sensor on its side, it snaps to like 89.9 or 90 degrees. So I have pretty good confidence in the tilt sensors, and being able to do their thing for a long time. I don't think they're going to degrade or drift or anything like that, like a humidity sensor might. But I don't know exactly. So I'll touch base with the team, and like all these questions, we'll put together a formal answer here and get them up on our frequently asked questions on the website. So you can look for that later, and if there's any changes to that, we'll let you know, and maybe be more specific on total lifetime of tilt sensor or something like that.
Great, thank you. Question about the cable length. So if the cable length increases, which is connected to sensor, can it impact the performance?
Not for a smart sensor, because the irradiance measurement, the analog signal that used to be measured, all we could measure 20 years ago, that's made immediately right at the detector in a circuit board. and put digitally. And the same is true for the tilt sensor and the internal humidity sensor and the internal voltage monitoring. That all gets digitized. And so whether when you go from 10-meter cable to 100-meter cable, you're still sending a digital signal. And if that digital signal comes across cleanly, you still get the value. It doesn't shift the values. It just, you either don't get data or you do get data kind of thing. So in a digital sensor, you're not going to have any issues with cable length. And maybe the question was a little aligned to analog sensors too. So since we have some time, I'll just jump into that. Somewhere between 10 and 100 meters, we don't see significant differences in irradiance values. That can be influenced by really, really harsh site conditions where you have a ton of electromagnetism, and we work in solar, so there can be a lot of noise in the site. I haven't had anybody really report that, hey, we had a 10-meter cable and we extended it to 100 meters and now this sensor is reading out of calibration. But when you start getting over 100 meters and you get really, really long lengths, say you're trying to go 400 meters on an analog sensor, you want to be careful about using voltage outputs for that, especially because the voltage outputs from a CMP10 are very small in the microvolts. And so changes that are influenced by current being induced on the cable and things like that can have significant impacts. And you might want to consider switching to a 4 to 20 milliamp for really long cables, or going to a digital sensor. And then for really, really long cable runs, like a kilometer, it might be more cost effective to just put in another monitoring, data collection monitoring type thing next to the sensor rather than trying to make a really long cable run. Hopefully that answers that question.
Great. Looking at the time, we still have time for a few more. So Damon, here it comes. Do you adjust the tilt seasonally, or it is fixed year round?
Not exactly sure what that question means, but I would say that you want your tilt on your sensor to be pointed in the same orientation as your average module. And so there are fixed tilt sites where they have a spring and a fall, or even a quarterly adjustment where they adjust the angle. And of course, you'd want to change your sensor at the same time. But I think that's maybe more few and far between now. And if you're thinking about a single axis track site, that's not going to have something where you need to change how the sensor is oriented relative to the modules seasonally, because you want the sensor to see what the modules are seeing. So it's more about keeping the sensor pointed in the same direction as the average of the modules than it is about trying to adjust for how the sun changes as you're measuring irradiance.
Great. There are so many questions coming in. Okay, let's go for
Great.
another one. You've presented a picture of Pyranometer without the feet.
Mm-hmm.
And one of the participants was thinking about it, but was worried about the sensor body heating up on the mounting plate. Do you have any thoughts about that? Is there
Yeah, so
anything to worry
that's
about?
why we offer fixed tilt feet, so you can still retain that air gap in there. Maybe for really hot environments, especially where you have like cooler nights and really hot days. And maybe, I'm not sure if the actual temperature range here in Logan is a good example of that, but here in Logan, it's about 55 Fahrenheit or 12 C at night, and 95-ish in the day, 95 Fahrenheit in the day, or like 35 C. So there's a pretty big temperature swing. And that change in temperature swing and how the sensor reacts to irradiance while it's changing temperature, if it's then has more conductivity with the racking around it, and the racking is changing temperature, that also influences the sensor body temperature. So that there can be influences on irradiance. However, especially with smart sensors, we're measuring detector temperature and we are correcting for temperature in the measurement. So as long as those temperature changes are not happening in like the 1 or 2 second rate, if it happens over 5 or 10 minutes, you're not going to see any kind of temperature impact. So you might see data in partially cloudy times, like some of the noise that you see there might be due to temperature changes, but being able to say that it was due to temperature changes would be extremely challenging. And I don't think, like, a lot of times the mounting plates are pretty thin and they're only mounted in a couple of touch points. So the actual conduction path down to racking or really hot modules, things like that, is still pretty limited. and you've got wind speed blowing and cooling not only the mount but the sensor. As you're thinking about that kind of complex thermal equilibrium that's going on, it's probably a best practice to keep the sensor with a little more of an air gap, but is it going to destroy your data if it's mounted flush like that? I'd be open to seeing data if someone has it that where they see an impact, but I would guess that there isn't.
Great. And in solar, have you seen many issues related to poor earthing of mounting plates or sensors?
Yeah, so pyranometers were invented 100 years ago, a little more, or almost 100 years, something like that. And solar PV, especially as a commercial industry, wasn't around. They were designed for being mounted on net station towers and understanding how irradiance reaches the Earth and the radiation balance of our planet, and how the environmental impacts of irradiance affect us and the weather and things like that. And so being on these remote stations that have a single grounding point, you don't really develop ground loops, and lightning strikes don't cause big current influxes across cables and things like that. Then you jump into a solar farm and you have sensors on a tower and sensors out in the array, and they're usually separated by 15 to 15 meters, 50 meters, 50 feet to 200 feet, something like that. And yeah, then if you ground at both points and you connect the middle, now you have a ground potential loop that can cause issues. And so making sure you have proper grounding in your enclosure, proper grounding of your digital communication, proper grounding of your sensor shield, proper grounding of your sensor housing, all of that is important. And there are a couple of different ways to skin that cat. So if you want to know more about that, come see us at RE Plus, and we'll talk about it more.
Wonderful. Um, I guess we can do two more questions. The next one would be, what would be the solution for aligning the pyranometer in the event that the bubble level evaporated?
So if you don't have a tilt sensor, like you have a CMP10 or an SMP10 that doesn't have a tilt sensor in it, you could use a torpedo level or a digital level. I happen to have a little square one here with me. Sorry for the brief absence there, but this is about the size of the edge of a sensor body. And so you could use that to try and fix something in a pinch. The other answer, of course, is when your bubble level expires, if you're sending it in for recalibration, that bubble level replacement should be part of that recalibration. And then if you have a sensor with tilt in it, the bubble level then becomes a little more of a convenient way to get a GHI sensor, but you can still access tilt data and get the sensor leveled. A little bit of a fail safe there.
Great. So that would be the last question for today, looking at the time. In a PV plant, the array or modules are not in one plane. What would be a recommended strategy to find the right spots for POA measurement?
So I think we've talked about this a little bit, and maybe this question comes from somebody with significantly more complex terrain than like a flat desert would be. Like kind of what you see in this questions photo is nice and flat, but there's lots of solar farms that are on hills or in mountains, and there's lots and lots of different tilt angles. Myself, the theory in my head says, well, I need to designate the radiance zones, and maybe I need more sensors than IEC might normally request in order to get my radiance data to match the number of zones that I have. And I would be trying to look for strings or array sections, inverter sections that I can capture with a single sensor, and I'd be trying to orient that sensor in the direction of the average of all the modules in that group. And then I would be trying to use the largest group that I can in order to use less sensors, because that's more economic for the site. But sometimes that's just not possible, and you have to add in more sensors. It's extra common in module soiling, for example, because soiling isn't uniform across sites. So if you have module orientation that's not uniform across sites, that's a reason why you may need more sensors.
Great. Damon, thank you so much for your time and for all the insights that you shared with our audience today. As I've mentioned at the beginning, the session was recorded. You are going to get the recording with the next email from us. If you have any questions in the meantime, just reach out. We are also at RE Plus, just as Damon said, in a few weeks. So we are happy to get into deeper discussions around your projects and any issues that you're seeing in your projects. And yeah, with that, I'm handing over to Damon to say goodbye and hopefully see you soon.
Yeah, thank you very much. Appreciate your time. Thank you for all the questions. Been good. Look forward to talking to you more. Have a good day.
Thank you. Bye.